Hello and welcome back to Calculus 3 on this glorious Wednesday evening. What are we going to do? Partial derivatives, right? 12-4. We studied derivatives before in Calculus 1, and we know that derivatives measure rate of change. So if you draw a curve for some function, you pick a point, it will have a tangent line, and steepness of that tangent line, which is the slope, is measuring the change at that point. So that change is measured over infinitely small interval. And we distinguish between two changes, right? We distinguish with the average change, which is change between 2 points, which was the secant line. So say that. Right? There was that kind of change. So change in y over change in x. That was the regular slope of the line from algebra. But then we are mainly interested in the slope of the tangent line, and that slope of the tangent line was generated by the derivative function. So what was the derivative in Calc 1? The derivative is a function which generates all of the tangent line slopes. That was the derivative. So if you say y is equal to x squared, or f of x, let's put f of x. F of x is equal to x squared, then f prime of x, which is the function, the derivative, would be 2x. So now, this is called the derivative, and what it does is it generates slopes of tangent line as you provide a location at which you want to look for that slope. So you say, I want to find the slope at 1. Obviously, 2 times 1 is 2. Slope is 2. You want to find the slope at 10. It's going to be 20, right? 2 times 10 is 20. So the derivative in Calc 1 was described as measuring the change in y, but it was a change at the instant, so over infinitely small period, infinitely small interval. Now we are moving to Calculus 3, where instead of having a 2D case, we are having a 3D surface. And here is the 3D surface. I'm taking this microfiber cloth, right? And I'm creating a 3D surface. So this 3D surface is going to have some kind of a formula, z equals, and then whatever blah blah of a combination of x's and y's we can come up with to describe this surface. Say x cubed times y squared minus x to the third sine y, whatever. Right? So whatever you come up with that describes this surface. Now what's important is to understand that this surface is a three-dimensional surface, right, which takes space, and then this surface has its shadow, its domain on the floor, and the floor is our xy domain, right, where we look at the region for the domain. So now that region will have all of the x and y points, and it also has x and y axes. So now what are these partial derivatives? If you think about it, I'm going to draw the domain, the pen again. I'm going to draw xy plane, which will house the domain for our function. So here we have xy plane, and this, let's say, this region R is the domain for our function. Now note that you have x and the y axes, and you also have a z-axis that is actually sticking right out of the page, right out of the paper, in this case, for those watching, out of the screen, perpendicular to the surface. So that's easy, simple to see for you, because if this is xy plane, then the z-axis would be poking out perpendicular to xy plane. So keep in mind that this z-axis is pointing up. And then there is a shape above that. So now you have the floor xy plane, which is what I have there. You have the domain, right? And you have some kind of a shape above that plane. What are partial derivatives? Partial derivatives would be the derivatives along these cuts. If you are to cut this shape with a sword or a chainsaw or whatever, you cut x-axis down and the y-axis down. These partial derivatives are actually Calc1 derivatives in x over x-axis and the y-axis. That's what they are. So they do have hyperbolic paraboloid in the textbook, and they have actual shape of that as a physical example, right? Two hills. So as you are looking at this, you see that these two humps, right? Two hills, which are these guys, right? And then you have these paths. Now, what is the derivative? The derivative will measure the steepness along these, say, walkways, okay? Now, these walkways are actually where the x and y axis are. So anytime you take a partial derivative, it only measures what's happening, the shape, along x-axis and along the y-axis. That's what they measure. So imagine now tangent line. Tangent line going like that. Tangent line going like this, right? For this point here, going this way. For this point here, going that way. Right? So you have a north-south in this case, and east-west, right? Which would be your x-axis and the y-axis on the floor. And these partial derivatives measure change along those directions. So in my case, here is the shape. Here's my tangent line. So let's say x-axis goes this way. Tangent line along x-axis would look something like this, right? That's the tangent line following the x direction, and then the tangent line following the y direction. So those are the partial derivatives. So partial derivatives will measure change along those traces that you would get if you are to cut the object above x-axis or the y-axis. So whatever function you get. Now in case the picture over there, you get parabolas, right? So you actually get 2x, let's say, and negative 2x as derivatives. Yes?
There's one for x and one for y?
Yes. And then there will be one for z, and then later on we'll have mixed partial derivatives. We'll do that all tonight. Yes?
So it's not like a derivative of z with respect to x.
It is. That's what the partial derivatives are. But you don't take partial derivative in respect to two variables at once. You have a partial derivative of z, which is the shape, right? This shape is z equals some combinations of x's and y's and sines and ln's and whatever else, right? So you will see now in notation, we will say partial z of partial x. That's the partial derivative in respect to x. Partial z, partial y. And then we'll have second derivative, mixed derivatives, and so on. So this over here will be domain. Okay. And those are the symbols we all understand. The What happened? Very good. So along x-axis, we will have partial z of partial x, and along y-axis, we will have partial z, partial y. Partial derivatives are using this as notation, some kind of crooked d. So you will have partial x, and you will have your regular dx. And then you have the other delta x, right? So you have all of these symbols that you need to worry about now. All right, so in a nutshell, what do? They measure the change along the x-axis and the y-axis for the 3D shape and that's it. What are the definitions for this? Well, first notation, and then we'll take a look at the theoretical part. So notation. Notation for partial derivatives is, as I noted, partial derivative of, come on, pen, you can do it. I know, see, differential equations pop up instantly. So partial derivative of z in respect to x can be denoted this way. And it can also be denoted as the f, and then you put the little x like this on the bottom. So that's another notation that it's used.
So I feel like for the partial fraction, does the thing in the sign, I thought it didn't make contact. Like I thought it was just like an open short.
Like this.
It crosses over? I thought it didn't.
No, it should end at the end, but there we go.
Oh, it ends there, okay.
Yeah.
It is! It looks like a 2, okay?
So partial z, partial y, also known as f and a little y. All right, now let's take a look at the theoretical part. So you remember the limit definition of the derivative with limit h goes to 0 of f of x plus h minus f of x divided by h. Well, we have exactly the same thing for the partial derivatives, except now we have two input variables. We keep the one that we are not working on constant. So what is the partial derivative of x? Partial derivative of x also denoted as of xy, also denoted as partial z, partial x. It's going to be the limit as h goes to 0 of f of x plus h comma y minus f of x comma y divided by h. So you see that there is no difference except you have the comma y everywhere, because this is technically just the Calc1 derivative, which acts now as x-axis, and the z-axis are creating what used to be x and y-axis before. Does that make any sense? Let me actually show another picture from the textbook. It's somewhere here. Okay. So this is also a very good image. Who did a good job on this? So first you focus on a sand pile. Okay. Now you take a sword and you cut that sand pile on the axis over here, and you have the line, right? And now you have the secant line between 2 points, and you have a tangent line once that point travels to, same like in Calc1. So in Calc1, you had a 2D, and that was the end of the world. So you had x and y, and you had dy dx. Now you have x, y, z, but when you make a cross section, right? When you cut through the when you cut the object, you are cutting it as x and z. So it's still 2D. You see that? It's x and z, or y and z. Morning. So absolutely no difference than from what you learned in Calc 1, because partial derivative is literally just a 2D cut in a 3D object, and we are applying what we know from Calc 1. Partial derivative in respect to y is partial z, partial y, is the limit h goes to 0 f of x comma y plus h minus f of xy over h. So these are theoretical definitions, right? To understand what this is, and then you just keep in mind that what we are doing is we are simply cutting the object above x-axis or above y-axis. It can be shifted also parallel to those axes. And we are looking at a change along the cut, whatever trace we get. By the way, the black line, the picture that you are looking at in the textbook, the black line is called the trace, and then the red line over here is the partial derivative. In this case, partial derivative of x, because this cut is parallel to x-axis. So it's at point A in x. So x equals A. This is the partial derivative f of x, partial z, partial x, computed at A. Well, it's computed at B as well, but x is the input in this case. So mechanics, I hope, are straightforward and you are able to understand. Now let's see how this works in terms of calculations, because you guys will be taking a lot of partial derivatives in this course throughout. This will not go away at all in this course. Partial derivatives everywhere. And then also differential equations will have some.
What is that called again? Difference quotient?
The formula is called difference quotient, yes.
Okay, and we learned that.
Well, first time you see difference quotient just as a formula is pre-calc 1, but then in calculus 1 is put in a concept of the derivative. Difference quotient, right?
Yeah.
All right, so let's find partial derivative in respect to x and partial derivative in respect to y for f of xy. Say you have x to the 5 minus y cubed plus 3, whatever. So if you look at these definitions, observe that when you're looking for a partial derivative in respect to x, this y stays unchanged throughout the entire process. Now, y is regarded as a constant because we are only looking for a change along x. If you're looking for change along x, the y value for that x is always the same number. So in the eyes of the derivative, partial derivative of x, y is a constant. And if y has its own term, well, what's the derivative of constant? 0. So it will die every time. If it's multiplied into x in whatever aspect, it will be copied because it's a constant. So remember, when you are taking the derivative of x squared, the derivative is 2x. If you're taking the derivative of 3x squared, it's 6x because you have to copy that 3. So now that y will be regarded as that 3. It gets to be copied if it's multiplied into the variable. So let's see. What is the partial derivative in respect to x? I'll put both notations. It's 5x to the 4th. Now y is constant in the eyes of x, so that's 0, and the derivative of 3 is 0, so we're done. That's the partial derivative. What is the partial derivative in respect to y? What happened? Negative 3y squared. Everything else would be constant because we are taking the derivative in respect to y. All right, next one. Again, find partial derivative of x and partial derivative of y for f of xy equal to 3xy cubed minus x sine y. Awesome.
As long as you're not thinking of
So this might look crazy, but this is actually insanely easy because we actually don't have the product rule in this case. If you're taking partial derivative in x, all of the y's are constants. You just get to copy them every time. So we have partial derivative of x, which is dz dx, is what? 3y cubed minus sine y. Awesome. It's going to take some time to get used to this because it does look different and weird in respect to what you guys seen before. But I'm just going to say, think of this y cubed as if it was
a constant.
what?
A constant.
Constant, yeah. So it's like it's not there, so just copy that. 3y is constant, copy, derivative of x is 1. Sine y is a constant. So that's the coefficient of x, so derivative of x is 1. Awesome. Now what's f of y? What's the partial of y? So partial of y, which is dz dy. Is the stream alive? Yep, good. So partial of y is, now we have to take derivative of 3y, y cubed, which is 3y squared. So 9xy squared. Right? 3 times 3 is 9? Okay. Minus, what is the derivative of sine y? Thank you.
Oh, cosine y.
I know. Sometimes I feel so lonely. I ask what's the derivative of sine and it's just crickets. So thank you. I know. Depression is so quick. Always around the corner when I teach.
What's the difference between this and this?
Eventually, in good time, young Padawan. We'll get there. We'll get there very soon. Let's go level by level. The spice level goes up. So now +1, okay? So again, find fx and fy, and we're going to have this wonderful, wonderful function. F of xy is equal to x squared e to the xy. Beautiful function. So figure that out. I'll be right back.
Oh, but I'm just asking. I was asking how to add it. I was literally simple basic shit. Why is the Y there? I don't understand.
Figure it out?
Why do you have that? You don't use one.
I do
You
for
always
algebra.
say speak of air.
No, the only classes that I don't teach this way are algebra classes, and I always in rush to get there, and I need that.
When do you have algebra?
Sorry?
When you have algebra?
No, it's tomorrow first thing.
How
I just
early
opened the
is
bag and I
first
see
thing?
that I don't have a red one.
How early is first thing?
It's 11.
Oh, that's
Not
pretty
barely
early.
anything.
I mean,
That's actually 6 hours after I get out.
6 hours.
small children, yeah, could do that. I'm like sat down before I was like, oh.
Did you discuss this with your peers? I'm going to go around and ask you to tell me what the other people's names are right now. Because, yes,
I know his name.
I know you know, but what's his name?
I feel like if
Yeah.
I say John, or like, I feel like John or Jack is a good guess for like.
I think you're the only person that everyone knows their name because
I don't know.
I don't know,
yeah, it's so easy for other numbers to kind of blind. So, do we all see the product rule for x?
Yes.
And no product rule for y?
Yes.
Beautiful. All right, so now execute. Okay, execute.
Okay.
So you have two functions that both have x, they're multiplied, therefore product rule. And then there's only one y, so there's no product rule for partial y. But there's definitely product rule for partial x. The product rule kicked in on good. That's coming up. Well, whatever we have.
Did I draw any pictures on the last test?
So, would that look
I feel like I didn't. That's so exciting. Awesome. What did you show me?
I'm so conditioned that he's going to post stuff like that I just disregard it. Yeah, you're right.
What am I allowed to do?
When you're trying to manipulate something, you say you're like.
I recognize it from before because they have all the motivation.
I understand.
You can check yourself. Just integrate.
but I'm not Spanish, that's why.
All right, let's take a look at this problem together. So I have partial derivative of z in respect to x we have product rule. There's multiplication between the two functions. Both have x. So copy first times derivative of the second, which is e to the xy, times the derivative of the exponent, which is just y. That's the constant, right? You should look at this xy as like 3x. So that y would be the chain. Plus, copy the second function, which is e to the xy, times the derivative of the first function, which is 2x. And now we make it pretty. We can factor out x e to the xy. And then what's left is xy plus 2. Eventually, we will be setting this to 0 and doing cool things. So. I know. Awesome. Partial derivative of z in respect to y is equal to, now there's only one y, therefore this x squared is a constant. We copy that. And then we have derivative of e to the xy is e to the xy times x, right? Because now the derivative in respect to y is the variable, x is the constant, so the chain rule will give us x. Simplified answer, x cubed e to the xy. One more example from homework. What happened? As I thought. Looking for something simple that you can do in 20 minutes. What happened? Oh, we got this. Look at this. This is going to be epic. Find who and hv.
You say H or F?
Hold on, I have to write this because it's. There we go. Beautiful example. Shouldn't take too long. Out of how many peppers?
What's the spice?
There actually is a scale for spiciness.
There is, yeah, but what's your, how many out of 3 peppers, out of 5 peppers?
Like, so that first one, it's like a unit one.
If it's out of 5 pepper spice, this would be like, I would say 3, 3.5. What's annoying? This is the time to look at your Calculus 1 notes. And if I need to leave you alone and discuss this without me present. Someone runs to the board, writes the quotient formula quickly. that's CNN. Thanks. Yeah. Did you get a laser tag?
I don't know.
Yeah.
Took a while to get to the light for the end.
Yeah. So like government meeting in California campus. Yes, no.
Only get it, meeting, put it stuff up.
I know. They gotta give us. I'll give it to you. I mean, I don't know if it's right.
You can't simplify anymore.
Here's my question.
Need economics or make it economics.
I just even know. I know, but it's in respect to you.
Yeah, I think it might be. Let's see. All right.
No,
So.
I saw you want to do the first one.
Quotient rule
Oh.
is embedded in the chain, right? Because there's a square root over the quotient. So what I'm going to do is I'm going to try and make this a little bit easier by turning it into a product rule, because it might be easier to deal with it. So this is what I'm going to do. So I'm going to take the numerator, because we know from algebra that if you have square root of a, b, it's a square root of a divided by square root of b. Now the square root in the denominator goes as negative 1/2. So we hopefully know all of that algebra that is associated with this. I'm going to erase this because I don't want it in final notes. So now, when we rewrite, so that was rewrite, we are going to start taking derivatives. So let's take a look at the who first. Partial derivative of h in respect to variable u. Well, we have a product rule, so copy the first one times the derivative of the second one, which is negative 1/2 u minus v to the negative 3/2, times the derivative of inside is just 1. Are we all good on that? And then there is a big fat plus from product rule. Copy the second one, which is u minus v to negative 1/2, times the derivative of the first, which is going to be 1/2 uv to the negative 1/2, right, when you subtract 1. And then times the derivative of the inside. Since we are taking derivative in respect to u, it's just going to be v. V is a constant, right? And the derivative of u is 1. This is wonderful. Now we just need to kind of put this in one statement. So to simplify this, I will put negative 1, so negative square root of uv divided by 3 u minus v to the 3/2, right, because it had a negative exponent, plus another division line. We have just v in the numerator, and we have a square root of u minus v, and there is a 2 there, and then also a square root of uv. There we go. I'm sorry? The 3. I don't know where's the 3. It's a 2. That's this 2. I wrote the wrong thing. What happened?
I thought you were going to say you weren't looking my way.
I wasn't.
If you use with like the quotient rule, make it look really different.
Well, I was about to do algebra to actually make it look the same.
Oh, you, okay.
So we can multiply by u minus v, which will get us the same exponents, right? So the first one stays as negative uv over 2u minus v 3/2 plus, and the second one now becomes 2, the square root of u minus v, and this will be the 3/2. But the issue is that we still have this root uv floating about. So what I'm going to do is I'm going to, oh, and there is a u minus v here. I'm going to now multiply numerator and denominator by I want to do that on the other one, right? To make them the same. So that's going to be just negative uv on that part. We have a common denominator now, so that's 2 times root uv u minus v to the 3/2. Now it's common denominator. There's a plus here, and then I have vu minus v squared. So these guys cancel, and I'm left with negative v squared divided by 2 square root uv. You can still rationalize. I just don't care anymore. That's it. We could still rationalize by time, right? uv square root. But then there is an, oh wait, oh no, that's minus. Doesn't matter. Okay. That's the first half of the problem. And the second one, you just do the same thing. Do I have to do it?
But then we have left the answer. Like, do we have to do all that, or do we just did it?
What are you going to do when you say equal to 0? The answer is just do whatever you think is, you know? But what do we do when it's equal to 0, right? Yeah, when you cross multiply and just get v equals 0, right? So, yeah. Lagrange multipliers are around the corner, I'll just say that much. And also min-max, and so on. Get HV at some point in life, which hopefully will be this weekend. We're going to move to the next concept, and that is higher order partial derivatives. Higher order partial derivatives would be the second and the third and the fourth and so on. So if I have f of xy to be 3x squared y to the 5th minus e to the x sine y, again, as long as you're not replicating the same variable in the term multiple times, then you're not going to have product rules and so on. So this is actually very easy because you have only one x per term and one y per term. So what is fxx? Fxx is the second derivative in respect to x, denoted as the partial of z, sorry, partial square of z dx squared. Same notation as before for Calc 1. And what the second derivative is the first derivative of the first derivative. Seventh partial derivative is the first derivative of the sixth partial derivative. So it's just the next derivative. So to obtain the second partial derivative, you have to obtain the first one first, which is dz dx, and that would be 6xy to the 5 minus e to the x sine y. And then you do another derivative in respect to x, which will give you this, and that gives us 6y to the 5 minus e to the x sine y. So it depends what functions you have, what survives, what dies. I will ask you to find now the second partial in y. So what's fyy?
Like, I wrote it down, but I was like, oh, I'm calculating. I'm going to I didn't think anybody else like that. It was just like, that's the one. Minus dx.
There's this really good documentary on Netflix, and I was watching like a random episode of it, and they related curvature to black holes in the universe. It was really interesting.
Cool.
Yeah.
See, class is already useful.
Yeah. Yeah, it was awesome.
This is your first step in understanding what Einstein did. This class is the first step. The smug look. The smug look was the best. Okay, let's find the first derivative first, which is hopefully 15x squared y. Ah, my pen died again. Hold on. (15xy to the fourth) or 15x squared? Thank you. Minus e to the x cosine y. Are we all green on this? Yes? Okay, good. And then we have the second partial derivative, which is 15 times 4. Awesome. X squared y cubed plus e to the x sine y. Good job. Now, obviously, making these questions really annoying is easy. Involve product rule, chain rule, quotient rule, on the third derivative and so on. It is very easy to make this really annoying. But the process in terms of, what to do is you find first derivative, then second, then third, and so on. But we have a new creature now, and that is called mixed partial derivatives. And that would be something like this. This is a fifth derivative, actually. But when you look at this, you have the first derivative you take is in respect to x. Then the second one, you take whatever the result you get, you take with respect to y. Then another one of y, then of x, then of y. So mixed partial derivatives would look like this. Now, obviously, we only deal with, second order partial derivatives, and we have a theorem. So say you have, let's find something beautiful. Cosine 2xy. So cosine 2xy. Let's find the mixed partial derivative fxy. Now we are going to need this because a formula for figuring out min and a max of a 3D function will depend on this. So if you want to find maximum for this, which is this point here, you will have the formula for this surface look something like that. And then the formula that you guys are going to use will actually have you compute this piece. You will have fxx times fyy minus fxy squared. That's the formula that we are going to use in a month or so, 3 weeks. So you have to know how to find this. So the first derivative you're going to take is going to be in respect to x, and then whatever result you get, you will get the derivative of that in respect to y. This is called a mixed partial derivative because obviously it has both x and y in it. So we first find fx because that's the first one in a string. What's the derivative of cosine? Very good. So this should be negative 2y sine 2xy. Are we all green on this? Beautiful. And now we will take derivative of that result in respect to y. And that would be what?
Negative 2 sine xy plus negative 2y x cosine y.
Y plus. It's
Well,
in negative
plus
4.
negative, so it would be minus. Sorry.
No. It's positive 4.
Isn't it partial once you take in respect to y? Don't you have to split it up into? Yeah, right.
It's a product rule. Nice. Okay, good. I do what I can.
You want me to take forward for you?
No, I'll do it. So copy the first, which is negative 2y. Derivative of the second, sine, it's a cosine, so 2x cosine 2xy. And then plus, copy the second, which is sine 2xy, times the derivative of first, which is negative 2. So we actually had to use product rule. And what we get here, when we factor everything, which, well, you can only factor -2. That's not that exciting. So just leave it, I guess. So we have -4xy cosine 2xy minus 2 sine 2xy. And such is life. Okay, now the major theorem that we are going to cover is going to say that the mixed partial derivatives fxy and fyx are always the same. That's a theorem that you hopefully have on your class prep, because it's a major theorem. I will ask you now to compute, and then we'll write the theorem later. So compute for the same function mixed derivative yx, and you better end up with the same answer eventually. So you will first find the y, and then you will do the rest.
No, opposite.
Oh, you mean,
Duh.
a lot of most people do that, actually.
Yeah.
I know a person in Europe who paid €1,000. That's more than $1,000.
Probably doesn't have the cards.
I had a really good
To put
step.
that much money in a
Game and not even have the cards.
I thought it was just a meeting.
Well, no, it's town hall meeting.
Thousand.
The guy that's here in the assumption for it. And they brought a llama.
There's a llama?
I wasn't joking when I told you that we were on CNN.
I know there's a llama. That's so exciting.
Wait, did you?
So should we quit the class and go pet the llama?
Yes.
Can we?
Field trip.
Wait, hold on. Wait, I don't get the
Let's see what Stream thinks about canceling the class so we can go pet llama at the protest.
Wait, how many people want?
Pool, yeah, let's pool everyone. No, there are 10,000 viewers. I mean, we can't just abandon that.
Yeah, I think.
I was like 8. No, I was in 8th grade, but yeah.
Why?
There was just a law.
Okay, let's take a look. The sooner we solve all the problems, the sooner we'll go see Llama. So let's.
Oh, wait.
The answer is -4xy cosine 2xy. I am sine.
Oh, that's interesting.
Obviously.
Tyler is in equal sign, so why am I saying
Yeah.
that?
Yes, they do.
So I hope you all started the problem with negative 2x sine 2x y. And then, oops, that's just, let me just box this final answer here. There we go. And then fyx, so partial of y followed by partial in x, is going to be, again, product rule, so copy the first, negative 2x times the derivative of the second, which is going to be cosine 2xy times 2y. And then we have times copy second, which is sine 2xy times the derivative of the first, which is negative 2. And now we just put this all together, negative 4xy cosine 2xy minus, supposed to be a plus there, minus 2 sine 2xy, which is exactly the same as the one we have above. So we can all go together. You don't have to go now. Yes?
So does the theorem work with going beyond 2? Like, if you want partial x, y, y, x, y, you could find like the 2x first and then 3y, and it'll be the same as you.
Are you just saying letters now?
Yes, he's just saying it. Yes. We only care about fxy and fyx because we are going to use it in the formula later on, as I said. So let's write the theorem for partial derivatives. So the theorem 12.4, that's the name. Theorem 12.4, if you must. Equality of mixed partial derivatives. So assume that f is defined on the open set D of R squared, and that fxy and fyx are continuous throughout D, then they are the same. So I will just say, in short, for practical purposes, now obviously you wrote this on your class prep, so you actually have the full statement. In short, mixed partial derivatives are the same. Now this can be extended, as Mike asked, can we have this for other derivatives? And the answer is yes. It actually brings out a lot of complications down the line because these are the only two possible ways that you can put x and a y. X first, y second, or y first, x second. Now, if you have, let's say, xxy, it can be xxy, yxx, xyx, right? So now you have actually 3. So it depends on, right? It will depend. Here, I'll write this. It's not crucial for our class because we are not going to use it. We are going to use this because in some cases one would be easier to compute than the other. But if you have, let's say, if you have this situation, then it would be the same as this situation. It will be the same as this situation. So you have 3 in this case.
So you have to have the same number of x and y equal.
Yes. Yes. The order doesn't matter in which you take the derivative.
Fy and fx are, they're not the same thing.
Fy and no, they're not.
Oh, that's not a mixed one.
No, that's a vanilla one, right? Cool. Now all of this in 3 variables.
Yay.
That's the spirit. Well, it used to be z equals function of x and y. Now it's w equals to function of x, y, z. So we have 3 variables in there. And now you can find partial w, partial x. You can find partial w, partial y, and partial w, partial z. We are going to use this a lot. A lot. So know it. Mechanics, absolutely the same. When you are taking the partial derivative in respect to x, y and z are constants. When you're taking partial derivative in respect to y, x and z are constants. And then partial derivative of z, x and y will be constants. Observe product rule, observe quotient rule, observe chain rule. Be careful about those things. That's the end of it. And then mixed partials are the same. Yes?
So if there's a W, why is it 4 variables?
Well, it's 3 independent variables, right?
So what makes this different from like the FXY?
Well, for fxy, what you have is z equals f of xy. So your domain, in this case, is 2-dimensional, and you have some kind of shape above that, so that creates 3D. This function here is the 4th-dimensional function. Now, what does it mean? Well, I can still have this here to be all of this, actually, okay? And then this additional variable could be temperature, for instance. Because when I have these 3, so think about this room, okay? This point right here has different temperature than the point next to the window, right? This is the same room, but it takes time for air to move around and mix. Plus, I generate a lot of heat. Okay, so yeah. So what's happening is this location in space has its x, y, and z component, right? So that would be x, y, and z in there. And then the W would be the reading of temperature, say 72 degrees. You go over there for different x, y, and z, it would be, let's say, 70 degrees, right? So 4-dimensional functions actually are used all the time because it could just be a temperature reading on a 3D. But you can talk about the density in a certain part of the 3D object, right, where it's denser in one spot, it's less dense in another, so that could be 4th dimension or whatever. So in mathematics, it's very easy for us because we don't have to worry about physical constraints. We just keep throwing in dimensions, right? And the number of letters and the number of axes that you are working with represents the number of dimensions. Now, whether it has a physical ramification, right, of something that we can see and touch, it's a different story, but it works. So, as I said, that z equals f of xy could easily be all of this, and then you have, those 3 give you the 4th. Yes?
I have a question. If axis, or whatever the plural is, are supposed to be perpendicular, how do you have
Well, see, you are thinking in terms of space because that's what you're mainly dealing with. But you can have as many as you want perpendicular ones. It doesn't really matter. You're defining perpendicular as 90 degrees in terms of the spatial orientation. But I can have a 4th-dimensional. We can construct those objects, but theoretically they exist. The 4th-dimensional cube, the hypercube, known as tesseract, right? It is the object that evolves, right, from having 8 cubes placed in the four-dimensional space to create this object. And it's kind of really bizarre because if you as a 3D creature are trapped in the four-dimensional cube, you would just perceive a cube. So technically for you would look like this room, but then you stick the hand through that wall and it comes out of this end. That would, yeah, that's how awesome it is. Because the four-dimensional space works a little bit different. So can you have it? The answer is yes, but you can't construct it in our space that it's based on, right, 3 dimensions. Now, we do have the string theory and all of the other mathematics that it's coming up later for those of you interested to look for other very, very small dimensions that are curled up and exist and do wondrous things. Yes?
So we use a lot of four-dimensional functions and stuff like that, just not four-dimensional space a lot.
Yes. So anything. So I don't know. What is the body mass index? The BMI formula uses age, uses weight, uses right height. Thank you. So there are the 3 input variables to give you the BMI, which depends on these 3. Right. So that's a 4D. Has nothing to do with space. Right. So as long as you are using few different things, and out comes the 4th, it's the 4D. It's not in a sense that, right, 4 dimension as 4 variables, not 4 dimensions as 4 spatial dimensions. We use, space is just one of the applications, and we are kind of drawn because we understand it, right? You touch, you see, you feel objects, right? You sit in a box, so you understand it very well. But it could be anything else. Yes?
For the string theory, you said it used 11 different things. What exactly? Like, what would you use? Like, I don't know.
Well, in order for mathematics to work out, you need it. Well, string theory is the candidate for theory of everything, so trying to unite the whole thing. Yeah. Guys, no matter how far the physics are, we're still a pathetic species. It is just sad to see someone really drool over, us driving 60 miles per hour, and having the speed limit because some people can't actually handle it. To go when you have a sun right there and you have a trajectory, right, which is the orbit, and there's the poor Earth going around. If you are to drive 60 miles per hour on this path, it will take you 1,111 years to go around once. You see how pathetic 60 miles per hour is? The planet Earth will catch up with you and kill you 1,111 times. That's on average, right? That's what 60 miles per hour is. Sad at best. Sad. So whatever we do, we can't even get to Mars, right? Which is, we have to slingshot. That's how pathetic our technology is. And if you think about it, what do? We are burning stuff up, right? That's how we propel. Our cars work on exploding dead plants and animals in the engine block. That's what oil is, right? The rotted plants and trees and leaves and animals from hundreds of thousands of years ago. That's what oil is. So we extract that, we refine it, and we explode it. And then we move our car at 60 miles per hour from point A to point B. And if you go 70, you pay a ticket, okay? This is how sad we are as a species, okay? To get to Mars, you have to wait for it to line up, right? So have the orbit, and then you wait for the Earth and the Mars and the Moon, and then you launch and you slingshot around the Moon, and you hope that you converted units because the planet doesn't have the, like you have feet in the United States and you have meters in France, so, this is how sad we are as a population, right? We are divided. We are fighting against each other. We are you know, looking at the race, we are discussing about race equality, sex equality. We are sad. And when someone says that there is advanced alien species, which there is millions of those probably around universe and galaxy, uh, they come here. Why? Why? There is nothing that they can get. If they have technology to fly, they could probably just make a good reality show out of this. Because if they caught any of the signals of our reality shows, I don't think that they would actually ever have the willpower to actually fire up their engines and come here to, not even to kind of conquer us, because that's how pathetic we are. All right?
I think you should talk to the theater. Go over it.
No, but we are not investing. This government has no vested interest in education, which is why we're paid the way we're paid, and you guys are paying as much for education. Where I come from, education is free. You have to be good, so you have to pass the tests to actually go to school, which is free. In the United States, if you have a heartbeat and maintain body temperature roughly 90s, here's the pencil. It's physics. Sit down, right? But then you have to pass algebra and so on. It's just, it's much different. My views of education are not conventional, and a lot of people get offended when I talk about it, my colleagues as well. But I'm sorry? Anyway, I am a part of it. I am the part of the problem too, like everyone else is. And, you know, just hoping that one day we're going to wake up and understand that, you know, the climate has changed and that the time on this planet is running out for us, and we actually have to move on and have to, you know, figure out, because we are close. It's minute to 12 in population size. If the carrying capacity of the planet is 10 billion, which some models predict, and we have 7.4 now, that's minute to 12 in terms of population. It's going to be very soon, you know, competition for food and resources, because that's what the carrying capacity is all about. You know what the word competition means. So, oh yeah, you can use bullying, yeah, sure. So, yeah, we need a lot of technology. We need a lot of education. We need a lot of STEM to actually expand throughout the universe. And, you know, it's just, I guess, Elon Musk, and then there is NASA there as well, and, you know, and then we have a Congress that has like collective IQ of 7 when you add them all up, because, you know, as much as they used to invest in science and education and everything in this country, that's how much they don't invest anymore. So United States used to be the leader in all of these things like particle accelerators and fusion and everything. It's not anymore because Congress didn't pass any of the projects, so they've been built in Switzerland and been, which I don't care about, because for me, I don't care if someone is from Switzerland or from United States or from, because I don't share the ideas of patriotism at all in any country. I'm not from here. I don't care about being patriotic about Serbia or America or any country. I just don't care about it. I'm above all of that. Above the race, above, I don't participate in any race talks in either kind of, or any sex equality talks or anything like that, because I'm above all of that. As a human, if you have a human-like thing, that's the only thing that I worry about. So if you are a human or you're not a human, you're not a human, I'll probably eat you. So that's the, you know, yeah, I go through a lot of energy, you know. So you might want to call me elitist, but I consider myself to be above any of those discussions. Above politics, above race, above equalities, above gender and sex, all of those kind of equalities or issues. I actually don't want even to acknowledge them, up to the point where I'm going to spend my time, because we have one goal, it should be one goal, and that is for all of that talk to immediately stop and actually not be brought up at all, and just have, it's a human, like everyone is equal as soon as they're born, and have that equality, and just have education, and from that point on, education that is meaningful, education that is, propelled forward. It's just, it doesn't, yeah, I can talk about this stuff, and it just irritates me all the time. So, yeah, you guys are now 0.5% at RVCC, right? You're sitting in Calc 3 class. This is Calc 3 class, right? You're sitting in Calc 3. You're 0.5%. That's your competition at RVCC. When you move to NGIT or any IT school out there, you're just going to be part of the 100%, because this class is called Elementary Mathematics at NGIT. Differential equations, elementary mathematics, because it is. There is another 20, 30 courses after this one. If you're interested to be, you got to know differential equations, partial differential equations, complex analysis 1, 2, numerical methods 1, 2, asymptotic methods 1, 2. And then you have graduate level for all of those courses. You have dynamics and, theory of the, just courses upon courses upon courses. Topology, yes, and everything else. So, this stuff, 1800s.
We're almost there, yeah.
I know. I will never forget the first opening line. Professor walked in at differential equations and said, "Welcome to the course, what puts you 150 years behind current mathematics." And I'm sitting at differential equations, I'm thinking, the hell? At that point in time, this school had one section of differential equations going every other semester with at most 10 to 12 students. Like, that's it. That's how many. And I was one of those, right? And walks in and says that. I said, wow, I still have 150 years to catch up and then make up new crap on top of that, right? That's where the PhD goes.
Where are you right now?
To be in this chair. To be a tenured professor at NGIT, you need 2 postdoctoral degrees. So you have PhD, and then postdoctoral 1, postdoctoral 2, and then you are on your merry way to become a full professor of mathematics in that department. That's 3 dissertations, okay? Yeah.
Catch all that straight.
Let's see if the stream is going. Probably. Yep.
All those 2 people.
2 people. Oh, Peter. So, yeah. Someone actually voted for llama, so I guess we have to go. Thank you, viewer. So, yeah, take these derivatives and then see what you can do with that, guys. We need to get some spaceships going on, get the hell out of this before this explodes, okay?
Hashtag vote llama. We need
Yeah.
to cut.
All right, so homework is online and in the book and anywhere else you find. It will say bye to the stream and go see the llama, okay?
Yeah.